So another example of the sequential move game here for practice that I built up. Sorry for this example. Like I said, under game theory, a lot of terrible examples do come out to play. We have Anna right here. Her two strategies are to go ahead and build a snowman or don't build a snowman. And player number 2 is Elsa, who has the strategies of letting it go or not letting it go. Remember, we read the table from left to right to detail exactly who's player number 1. Anna is player number 1. Elsa is player number 2. We see these payoffs right here. The first numbers goes towards player number 1, who's Anna, so 60, 100, 40, and 10. And the second numbers are going to go towards player number 2, who is Elsa, so 30, 60, 90, and 10. They're all correlated to Elsa. However, in order to solve out for the Nash equilibrium, we need to use backwards induction. We go from right to left in order to see what the best strategy is going to be for each of these players. So as we read from right to left, on the top half of this tree right here, we hit Elsa first. What would be the best thing for Elsa to do? Would she want to let it go, or does she want to not let it go? So we're comparing this 30 versus the 60. So obviously Elsa wants the highest payoff. So what she wants to do is not let it go. So therefore, we underline that. We draw an arrow telling us that if Elsa ever reaches this part of the tree, she's not going to let it go. And we prune off or trim off the let it go strategy. We do the same thing on the bottom half of this tree. If we reach the bottom half of the tree, what does Elsa want to do? What's the best strategy? Should she let it go or should she not let it go? We compare the 90 versus the 10. Remember, the second numbers correlate to player number 2. So here, Elsa is going to choose let it go. 90 is bigger than 10. We prune this off and says, hey, if we ever reach the bottom half of this tree, Elsa's going to let it go. Next, we keep on reading the tree from right to left. Then we hit player number 1, who is Anna. And Anna has the strategy of building a snowman or not building a snowman. If Anna chooses not building a snowman, she knows for sure that Elsa is not going to let it go, and she'd get a payoff of 100. So Anna would get the payoff of 100. If Anna chooses don't build a snowman, she knows for sure that Elsa's going to let it go, and that is only going to lead Anna for a payoff of 40. So therefore, Anna knows exactly what Elsa is going to do at both of these branches because we have perfect information. So therefore, Anna is going to choose build a snowman because it's going to give us the highest payoff for her of 100 compared to the 40 than if she chose don't build a snowman. So here, she prunes that off, and that's exactly how we come to our Nash equilibrium. Anna's going to go ahead and build a snowman. Elsa is not going to let it go, and this leads to a payoff of 100 for Anna and 60 for Elsa. So here, we have these two underlined marks once again. This is seen as our Nash equilibrium. And once again, neither player can do any better by changing his or her strategy at this Nash equilibrium. This is the sequential move game, not as common as a simultaneous move game, but as you can see, the strategies are just a little bit different, the methodologies. Remember that we use the best response technique with the simultaneous move games, and with the sequential move games where one player moves first, another player moves right after him or her, that's where backwards induction comes into play. We'll wrap up the final games that we take a look at in this chapter in the next video.